Okay, so what is the density of NO2 at 200 degrees Celsius and 600 torr? Well, we can do this now. We know our PV equals nRT. Where do we get the density from?
Didn't you do something to the moles before?
That's right. We changed the moles. What did we change it to?
Let me look at my notes. Oh, you put in there grams over the molar mass, or grams per mole.
That's right. So N can be equal to grams over grams per mole. All right? So to answer the density, to solve for the density, we need the molar mass there, right? But now we can do that. PV equals nRT, N being expressed in terms of grams over the molar mass. All right? And in this, we want to solve for the density, so we want to switch the volume over here. So the pressure times the molar mass, I'm just rearranging everything, this is the molar mass, equals the density like that, and then this would have to be divided by temperature and the gas constant. Okay? Now we're not going to finish that one up. You can try it at this point. Essentially what we have is the pressure times the molar mass divided by the temperature divided by 0.0821, right? And that's going to give us the density of the gas. The molar mass is going to be that of NO2. The pressure, 600 torrs, needs to be converted to atmospheres. Temperature, 200 degrees Celsius, has to be converted to Kelvin by adding 273, right? All right, so I'll let you guys finish that one up, see if you can get it right. All right, 0.935 grams per liter is the answer. Hopefully you worked through that one and got it right. Okay. So we can calculate this, the volume of 1 mole of gas at STP. We already know what it is. Do you know what the answer to that is?
It was 22.4, right?
That's right. 1 mole of gas has a volume of 22.4 liters. And we can show that now with our ideal gas law, PV equals nRT, right? Pressure, 1 atmosphere. Volume, that's what we're after. Moles of gas, 1 mole of gas. R, 0.0821. That's liter atmospheres per mole Kelvin. Temperature. Now, this is something that we always kind of have to remember, that the temperature of a gas, the temperature at STP, standard temperature and pressure, is 0 degrees Celsius, 0 degrees, or 273 Kelvin. Now, there's nothing standard about that in terms of the temperature outside. In fact, when somebody refers to standard temperature, they're usually referring to room temperature. But when they refer to standard temperature and pressure in that way, STP, they're talking about 273 Kelvin, or 0 degrees Celsius. All right, so that's where we get our 22.4 liters from. All right, here you can use the ideal gas law to identify the PV and RT. To identify, it's a good practice. Why don't you guys go ahead and do this and try to find out what the density of helium is. Okay, so we just ran through one of these. So if you can't remember how to do this, you can go back a little bit and see how we identified the density. The answer here is B, 0.19 grams per liter. Good. Hopefully you took a chance to practice that one. All right. What is the mass of the sample? Sample of fluorine gas occupying 275 liters. PV equals nRT. N can be expressed in grams over the molar mass, right? RT, PV. What is the mass of this sample? 0.275 is our liters. Pressure, 950 torr. So 760, 945, 760 torr is 1 atmosphere. So we want the in atmospheres. So 945 divided by 760, 1.24. All right. The molar mass, we're going to move the molar mass over here too. Fluorine gas, that's 90 times 2, 38. All right, 0.0821 is the R. And then temperature, 72 plus 273, 345. All right, so all this will equal then grams. Okay. Excellent. Here's another good one to practice. We just did one just like this, so I'll let you guys take this as an opportunity to practice. I'm not going to go through this one though, okay? All right, make sure you push pause and do it. And if you forgot how, here's the equation right here, and you can figure that out. You can go back and look at that other one. Okay, good. One more to practice. Push pause, solve it. Okay, I'm going to show you the answer. Okay, so hopefully you got 11 grams per mole for the answer there. All right, so there's also the ability to express pressures in terms of partial pressures. And what this essentially means is, for example, if I blow up a balloon, so here's my balloon that I just blew up with my very own breath. All right, if I blow up this balloon, I'm blowing it up with the air around me. I suck it in and then I blow it into the balloon. So in this balloon, I have essentially air. What's in air again?
Nitrogen and oxygen. Is there some carbon dioxide?
Yeah, a little bit of carbon dioxide and a little bit of argon. Very small amount of carbon dioxide and argon. But it's essentially, let's say, 80% nitrogen and 20% oxygen gas. All right. So inside here is 80% nitrogen and 20% oxygen gas. And if I say that my balloon is at 1 atmosphere, then contributing to that atmosphere is 8/10, 80% is the nitrogen gas. So it's 0.8 atmospheres of nitrogen gas or 0.2 atmospheres of oxygen gas inside this balloon. So if you have the total pressure, then you can have what are called partial pressures contributed by whatever the different components are in there. Does that make sense?
Yeah, that's straightforward.
All right. So if I put 520 millimeters of mercury worth of gas from nitrogen and 250 worth of oxygen into an empty gas cylinder, what's the overall pressure of the mixture? It would just be the sum of those two, right? Because these are partial pressures, and so the sum, the resulting pressure, would be just the sum of those two pressures. Now, if I knew the partial pressures, or the pressure that's contributed by one of the gases, and I knew the mole fraction of that gas, then I could identify what we call the, I could identify the total moles that are in the compound sample. I could also identify the mole fraction of the other gases, all right? Or in other words, how many moles there are in the different, of the different gases in that container. So, N being the moles of gas, and X being the mole fraction of a given gas. So, the mole fraction, in this case, the mole fraction is just how many moles are of one the species relative to the moles total. So the mole fraction of nitrogen in this gas is 0.8. Now, fractions aren't percentages. They're just out of, if you think of it as 1 being the total, then 0.8 would be the mole fraction of nitrogen, and 0.2 would be the mole fraction of oxygen gas. And if you take the mole fraction of something times the total pressure, it'll give you the pressure or the partial pressure of whatever gas that is. Okay? So simply put here, 1 atmosphere is my total pressure. Then that total pressure times the mole fraction of nitrogen, 0.8, will tell me that my mole fraction is 0. Let's see, did I do that right? Oh, no, sorry. This is the total pressure over here. Yeah, that's right. If my total pressure is here and my, total pressure here, mole fraction there, total pressure 1, mole fraction there, 0.8, and then I'll get my fraction of my my partial pressure of my nitrogen. Okay. So this is my mole fraction of nitrogen, and this is the pressure of the nitrogen gas, and this is the total pressure. Let's do some of these. What's the mole fraction of nitrogen gas in the atmosphere if, this is our atmosphere, 0.78 atmospheres of nitrogen, 0.2095 atmospheres of oxygen, 0.00093 atmospheres of argon, and this small value of atmospheres of carbon dioxide? Well, the mole fraction is equivalent to its partial pressure if we just have 1 atmosphere of air. So 0.7808 will be my, not just my partial pressure, but it will be my mole fraction because my total pressure is 1 there. Okay? So the mole fraction is going to be equal to the total moles, the moles of my material divided by total moles. Okay, so in a mixture of gases, there's 5 grams each of these different gases. What's the mole fraction of neon if the partial pressure of neon in the mix is 1 psi? And then what's the total pressure? So let's do the mole fraction first. Mole fraction. To get the mole fraction, I just need to know the total moles. So N total moles. And I need to know what fraction is my neon, because that's what I'm after. So I want to know the moles of neon over the total moles. And I can find the total moles by looking at how many moles of neon, how many moles of oxygen, and how many moles of hydrogen I have. How many moles of neon are there?
Well, you got 5 grams of neon.
That's right. So with 5 grams of neon, how would I do that?
Well, just divided by the molar mass, right?
That's right. So we got 20 grams of neon for every 1 mole. So we got 5 divided by 20, 0.2 grams, 0.25 grams, moles of neon. All right. How would I do it for oxygen?
Well, same thing, just divide by 32.
So 5 divided by 32, that's the molar mass of oxygen. 0.156 moles of oxygen gas. And then what?
Same thing for hydrogen, just 2. So 5 divided by 2.
2.5 moles of hydrogen gas. So I got 2.5, 0.156, and 0.25. All right? So I'm going to take my 0.25, add them together. 3 moles of gas total, 3 moles total. And then to find my mole fraction, I take the moles of neon and divide it by the moles total. How many moles of neon did I have?
0.25.
That's right. So 0.25 total, 3 moles, right? So 0.25 divided by 3 should be my mole fraction. 0.083 is my mole fraction of neon. Okay? So if I know the mole fraction of neon, and I know what they say here is the partial pressure of neon, right, is 1 psi, what's the total pressure? Well, if neon is just contributing that many moles out of the total moles, right, you can take your mole fraction and multiply it by the partial pressure, right? So mole fraction multiplied by the total pressure, and that will equal the partial pressure. So if I have the partial pressure here, set it equal to the mole fraction times the total pressure, right? So my mole fraction times the pressure total will equal the partial pressure of my neon. And if I'm told the partial pressure of the neon is 1, and my mole fraction is 0.083, I can solve for the total pressure there by taking 1 divided by 0.083. So 12 will be the pressure, the total pressure. Okay? So, again, we found the moles of neon, the moles of oxygen, the moles of hydrogen, added them all up. That's how many moles total there were. And we took our mole fraction of neon, 0.0861. Oh, they got a slightly different value because they use probably for hydrogen, we use 2.5, they use 2.48. Okay, so it's just a slightly different value, but we still end up with only using 2 significant figures, the same value. All right, good. So, for a mixture of gases, the total pressure is the sum of the contribution of all the gases, giving us a little reminder there. In a mixture containing 5 grams of each of those, what is the total pressure at 50 degrees Celsius in a 25-liter vessel? So, what do you think, Fred?
Well, we just did this, right?
Yeah, we did. We just looked at our moles of the different materials. So we have a total moles of 2.88, and the moles of the neon is 0.248, right? So moles of the neon is 0.248. Total moles, 2.88. So how is that going to help us?
Well, if we want the pressure at 50 degrees Celsius in a 2.5-liter vessel, isn't that sound like using Pervner?
I think that's right. How can we use Pervner?
Well, we know the total moles of everything, 2.88.
Okay, 2.88 is our moles.
R is 0.0821.
What's our temperature?
50 plus 273.
Okay. 323.
And 2.5-liter vessel.
2.5 liters. So that leaves behind the pressure. So if we have 323 times 0.0821 times 2.88 divided by 2.5, 30.5 liters. 30.5 atmospheres. 30.5 atmospheres. Okay. Good job, Fred. All right, good place to stop.